Today we are going to start our first lecture, and the paper is Mathematical Physics 1. So let us start. So the first topic in mathematical physics is plotting. So what is plotting? So what do you plot? So you plot a function. Okay, so you plot a function like y is equal to fx. You plot a function. That's what plotting is. So that means you have to, so what is y, what is x? So these are the coordinates in 2 dimension. That is, in order, so this is, okay, so this is so this is my x and this is my y. And y and x are perpendicular. So this axis x and y are perpendicular to each other. That is, this is 90 degree. This angle is 90 degree. So in order to, so this is called Cartesian coordinates. We learn other types of coordinates also. This is the simplest of coordinate systems. So this is Cartesian coordinates. So in order to define a point in 2-dimensional space, so you need two coordinates x and y. So this is in 2-dimensional space, 2D. And what does y is equal to fx signify? What does it signify? It signifies a curve that is like this. So let us draw again. So this is your y-axis and this is my x-axis. Okay, and you just change the color. So this is my x and this is my y. So what is y is equal to fx? Y is equal to fx is in 2 dimension, it can be a curve like this. So this is my y is equal to fx. So this is my y is equal to fx. So this is a curve. So this is what it signifies. It's a curve in 2D. This is important in 2D. In 2 dimension, y is equal to fx is a curve in 2D. You have come across this before as straight line. Like for straight line, what do you write? Y is equal to mx plus c. Right? So m is the slope and c is the intercept. So if I again draw my coordinates like this, then y is equal to mx plus c. So this is your y coordinate and this is my x coordinate. So y is equal to mx. What is y is equal to mx? It can be a straight line like this. So in general, y is equal to fx. So this is in this form. So this is in the form of y is equal to fx, right? So y is equal to mx plus c is a very specific type of curve. In general, which is a straight line. In general, y is equal to fx can be a curve like this. Okay. So in order to draw a curve, what do we need? So I want to plot y is equal to fx. So what I need to make a table. So plotting is important. So let us again change the color. Okay. So I want to plot. So how do you plot? Plotting. So plotting. How do you plot? So you are given y is equal to fx. So you have to make a table. So you have to make a table like this, right? So one column will be x, other column will be y. So you fix x, and corresponding to that you find the y from the relation, this relation. Okay, so you can find out y. Similarly, you go to another x and find out the corresponding y. You go to another x, find out the corresponding y. You go to another x, find out the corresponding y. So you keep on doing this, you get a series of points. And then what you do? You take a graph paper. So what you do? So how do you plot? One way of plotting is you take a graph paper. You take a graph paper and plot the points. So these are the points what we have, x, y coordinates. So you take the graph paper, plot the points, and you may get something like this. Okay, something like this. So you may get something like this. So it may be like this. So you have got a plot. But nowadays we don't use graph paper, means this is obsolete. We don't use that. So what do? We use software. So what do? You have the function y is equal to fx. So you have a software. You have software like GNU plot. Okay, you have software like GNU plot, or you have software like MATLAB, which will do the job for you. So you don't need graph paper, you need computers, and you need the proper software. So you will feed this y is equal to fx to the software, say GNU plot, and you will get the output. You get the curve. So you don't need graph paper. That is how you plot it. Or you can use MATLAB also. And these kind of softwares have many uses. So these kind of softwares are very useful. Okay. So this is two-dimensional. So two-dimension y is equal to fx is a curve. So if you go to 3-dimension, then what happens? So we are now talking of 3-dimension. So 3-dimension. So 3-dimension, what do you need? You need 3 coordinates: x, y, and z. You need 3 coordinates to define a point in 3-dimension. So that means you have this kind of coordinate system. So this is 3-dimensional. So this is my z-axis, this is my x-axis, and this is my y-axis. That is the convention. Okay. So this is z-axis, this is y-axis, this is x-axis, and this is y-axis. right? So using this coordinate system I can define any point in 3D. Now in 3-dimensional, if I write z is equal to some function of xy, what does it mean? Is it a curve in 2 dimension? Does it imply a curve? So if that, does it imply a curve? No, it does not imply a curve. So z is equal to fxy implies a surface. It implies a surface in 3 dimension, in 3D. So we will see that, we will do these examples in 3D. Okay, so another way of writing this is z minus f x y is equal to 0, or I can also write this as some function of x, y and z is equal to 0. Okay, correct? So this thing can be substituted by another function f x y z is equal. So this is also what it defines a surface. Okay, and another thing that I want to mention here is this order is important. Like I will not use this kind of coordinate system like z. Say this is x and this is y. Okay, so here I have just interchanged x and y here. So here this was x, this was y. Here I have this is x, this is y. So this kind of thing we are not going to use. This kind of coordinate system we are not going to use. Okay, so this is not. We will use this kind of coordinate system. So this is called the right-handed coordinate system. Right RHS. Right-handed system. This is the right-handed system. Why? So this is the convention. We always use right-handed system. What is the significance of right-handed system? Like if you rotate from x to y, okay, if you rotate from x to y, then imagine you have a screw. So you are rotating a screw from x direction, from x to y. Then in what direction the screw will advance or move? The screw will advance in this direction, in the direction of z, right? So this is the convention. So this is the coordinate system we use. So this is called the right-handed. So if you rotate a screw from x to y, then the z-axis direction will be such that the screw will advance in the direction of the z-axis. Then only we use only that kind of coordinate system. Whereas here you see, if you rotate from x to y, okay, then what happens? The screw will not go in this direction. It will not go in this direction. No, it will not go in this direction. Screw will not go in this direction. The screw will go in the opposite direction. The screw will go in this direction. If you rotate a screw from x to y, then the screw will go in this direction. So it is going opposite to the direction of z. So we won't use this kind of coordinate system. We will only use this kind of coordinate system. So this is called the right-handed system. Okay. So in my whatever you are going to see now, the plots. Most of the plots I have drawn using GNU plot. So this is the software I have used. Okay, so let's go. So this is a plot of sin x. So what I have plotted here is sin x. So you may not be able to see clearly. So this is my y-axis and this is my x-axis, and my function is y is equal to sin x. What is the maximum value of sin? So whatever sin x is, sin x always lies between this, isn't it? Between -1 and +1. So you can see at 0, at x is equal to 0, so this is my 0 coordinate along y-axis. This is the 0 coordinate along y-axis, and this is the 0 coordinate along x-axis. Okay, so you can see at x is equal to 0, y should be 0. So here this is the point. Okay, and again at x is equal to pi by 2, sin pi by 2 is 1. So this is pi by 2. So this coordinate. So this is, you can see 1. This is 1. So sin 0 is 0. Next is sin. So this coordinate is x coordinate is pi by 2. Okay. Sin 0, then sin pi by 2, then this coordinate is, what is this coordinate? Again it is come to 0. So this is sin, so this x coordinate is pi. Is it not? This x coordinate is pi. And then it becomes, here it becomes -1, and then again here it becomes 0. Okay, so this is coordinate is 2 pi. So this coordinate is 2 pi. Right? So this is sin 0 is 0, then at sin pi it is again 0, then again sin 2 pi it is 0. So you can see here it goes up. So you can see that it's going up and then it's coming down, attains 0, goes down, and then it again reaches 0 and again goes up. So there is repetition. So let us change the color here. So you can see here it's going up and it's again going down, it reaches 0 and it goes like this, and again it reaches -1 and again goes up and reaches 0. So this is called, it completes one cycle. So after that it repeats itself, is it not? It's so from here it changes, it repeats itself. So there is repetition after this. So sin x is after this again there is repetition. So what we can say, sin x we know is a periodic function. Sin x is periodic. Sin x is periodic. So let's see what it means. That means sin x plus 2 pi is sin x. Sin x. That is, it's repeating itself. Repeats itself repeats itself after every 2 pi. Is it not? You can see that x plus 2 pi, if you increase x by 2 pi, it repeats itself. Its periodicity is not pi because sine x plus pi is what? Minus sine x. Is it? So this is so this is not the periodicity. This is not the periodicity. It does not repeat itself. It comes with a minus sign. So this is the expression that tells us that sin x is periodic and it repeats itself after every 2 pi. Okay? So this function which I had drawn here has a period 2 pi. Now we have drawn another function here. So this is y is equal to sine 3x. It is very similar to the other sine function I have drawn. So here you can see the sine function here, this is minus 10 and this is plus 10. So this function has been drawn between x is equal to minus 10 and x is equal to plus 10. Here also the same function has been drawn between x is equal to minus 10 and x is equal to plus 10. But here you see it is very dense, it repeats itself. So here the repetition of the function is more than this self. Right? So here repetition is more, isn't it? So sine 3x repeats more than repeats more than sin x. That's clear from the graph. Sine 3x repeats more than sin x. Okay, let me erase it so that so this more than sin x. That means, what do I say? It's so sin 3x repeats, you can see it repeats itself more than sin x. That implies the period of sine 3x is less. It is less. So the period of sine 3x is less compared to sin x. So let's see. So that means, so let us see. So let us consider sine 3x. Okay. So sine 3x. Okay. So if I increase the value by x by value by 2 pi by 3, okay. So what I have done is sine 3 bracket x plus 2 pi by 3. What is it? This is, if you just open the bracket, then it is sine 3x plus 2 pi. And this is actually equal to sine 3x. That means, so this implies the periodicity of sine 3x is 2 pi by 3 and not 2 pi. Okay, 2 pi is for this is for sine x, and this is for sine 3x. So you can see the periodicity has decreased. Now it's 2 pi by 3. So in general, if I write sine k x has a periodicity of 2 pi by k. You can easily check it. So if you increase x by x plus 2 pi by k, then you will find a similar relation. You can work it out yourself. Okay. So before we go to the next plot, I just wanted to mention one more thing which I did not mention here. So when you are talking of this coordinate system x, y, z, so you have two plates. So in this coordinate system you will have the zy plane. You will have the zy plane. Zy plane is actually also known as the x is equal to 0 plane, because on this plane, on the zy plane, x is 0. Then you will have the xy plane. Xy plane is, so this is the zy plane, this is the xy plane. Okay, so the xy plane, x, y, the xy plane corresponds to z is equal to 0. That is, on the xy plane the z coordinate is always 0, on the zy plane x coordinate is always 0, and then you have the xz plane or zx plane, whichever we want to. On the zx plane, which coordinate is 0? Y coordinate is 0. Okay, this you should remember. So this is the zx plane. On this plane is a flat surface. On this plane, y is equal to 0. Okay, on the xy plane, z is equal to 0. So when you go to this coordinate system, xy coordinate system, actually here z is 0. So I can write, so this xy plane actually is also, I can write it as z is equal to 0 plane. Okay, so this is also known as the z is equal to 0 plane, xy plane or z is equal to 0 plane. So we go back to our plot. So now we are plotting another function, y is equal to cos x. So this is similar to, sin x, but cos is a different function than sine. So here also you may not be able to see. So this is my y-axis, and this is my x-axis. This is the 0 on the y, and this is the 0 on the x, and again this is minus 10 on x-axis, this is 10 on x-axis. And you can see that at x is equal to 0, cos 0 is 1, so you can see perfectly. Okay, and again for cos x also, cos x is a periodic function. We know that cos x is just like sine, cos x is a periodic function. Okay, just like sine. Whatever argument I gave in the case of sine, the same thing is valid for cos also. You can take any here, you can start from here. Okay, so here it is maximum, then it goes down, then it goes up, again reaches maximum, and starts going down. So this, it has a periodicity. So this is 2 pi. This is 2 pi, just like in sine. So this is 2 pi on the x-axis. So cos x is a periodic function with period with period 2 pi. That is, after every 2 pi distance the function repeats itself. So I can write like this. So cos x plus 2 pi is equal to cos x. Okay. So that implies that it has a 2 pi period. Okay. So now we go to the next function. This is again we are plotting here y is equal to cos 3x. Okay. And again here I have my y-axis, and here I have my x-axis. Here is the 0 on the x-axis, here is the 0 on the y-axis, and here is the minus 10 on x-axis, and here is the 10 on x-axis. So compared to, again you can see, compared to cos x, this cos 3x changes more frequently. So cos 3x changes more frequently. Let me just use the eraser. So cos 3x changes more frequently than cos x. So I can say that the period of cos 3x is less, and I can use the same logic. Cos 3, and if I increase x by 2 pi by 3, So what I get is, what do I get? Cos 3x, okay, cos 3x plus 2 pi, and this is again we know is cos 3x. So just as in the case of sine, cos 3x has a period of 2 pi by 3, which is of course less than 2 pi, is it not? So 2 pi by 3 is less than 2 pi by 3 is less than 2 pi. This was the period for cos x, and this is the period for cos 3x. And now we can go to so here we are plotting, our function is y is equal to tan x. Tan x is different. Here you know that you can see from here tan 0 is 0, we know that. So tan 0 is, so tan 0 is 0, and so you know tan is increasing function, so tan pi by 4 is 1, tan pi by 4 is 1, so like that if I go 1, and like that if I try to approach infinity, then tan pi by 2 minus epsilon, okay, limit, so we will take the limit epsilon tending to 0, how much it is? It goes to infinity, right? So this is what is showing here. So this is 0 is 0, then this is, so this is 1 corresponds to pi by 4, and as I approach pi by 2, so this is like pi by 2, you can say this is like pi by 2. So this is the pi by 2 axis, so this is the pi by 2. So as it approaches pi by 2, what happens? It becomes infinity, it diverges, okay, and you know that tan of negative is always negative, so you can see it's like this. So tan of minus pi by 2 is, it will be minus infinity. So here so this is like, so this you can, so this one you can write it as, so this one, so this one is like minus pi by 2. So when it's approaching pi by 2 from this side, from the left hand side, it diverges, and when it's approaching minus pi by 2 from the right side, it also diverges, but in the negative side, because this is negative, this part is negative. So this is my y, and this is my x. Okay, so y is increasing in this direction, so 1 2 3 4 like that, it goes towards infinity, and decreases in this direction, that is -1, -2, -3, and then like that it goes to -infinity. So between -π/2 and +π/2, this is how the tan function behaves. But what about, say, π/2 to 0? In this what happens? So let's see. We know that tan π/2, so π/2 plus epsilon is minus cot epsilon. This is a standard relation. Okay. So if I take the limit epsilon tending to 0, then what happens? So what is cot 0? Cot 0 is infinity. So this one tends to -infinity. Tan 0 is 0, so cot 0 is infinity, so this one becomes -infinity. So if you increase tan, so that means if you just cross, so you can see here, so if you just cross, so if you can extend this one like this. Sorry, you can just extend like this. I hope you get the point. So here it's going to infinity, and as soon as you cross the π/2 line, this is the π/2 line, on this side it is -infinity. So from there it is -infinity, and then it goes to 0, and again it starts rising, and again it goes to +infinity at what? 3π/2, isn't it? At 3π/2. So this is the 3π/2 line. So you can see from the behavior that tan x is also periodic. So tan x is also periodic, but now there is a catch here. What is the period? It is pi, because tan x plus pi is equal to tan x. So tan x has a period pi. This you can check from here. So you can see, so this is pi, because you can see from here. So suppose I start from here, so I go up and I reach infinity. Okay, then I still keep increasing my x, then suddenly there is a jump. So here again we have -infinity, so -infinity, and then it comes down from -infinity, then it reaches 0. So here I started from 0 and reaches 0, and then it again starts going up. Okay, so you can see this period is pi. So this distance is pi. This distance is pi. What is pi? Pi is approximately 3.14. So this distance, this is, after this the function starts repeating itself. It's clear from the graph. Okay, and we now go to exponential point. So here what we are plotting is y is equal to e to the power x, and this is my y axis and this is my x axis. So as x tends to minus infinity, y tends to 0. Okay, and as x tends to infinity, y tends to infinity. Means y keeps growing. So you can see here, so here exactly what, so on the left hand side x is decreasing here. So here you have infinity, so it's starting from 0, it's starting from 0, then it's going up. Okay, so this is 1. So at x is equal to 0, x is equal to 0, y is 1. So this is, so this is, sorry, so this is like, this is my, so when x is equal to 0, y is 1, this is the 1, and then as you go beyond 0, it keeps increasing, and it keeps increasing. That is, there is a divergence. So this is y is equal to e to the power x, and this is y is equal to e to the power minus x. Here it's just reversed. So this is my y axis and this is my x axis. So here as x tends to infinity, y tends to 0, and as x tends to minus infinity, y tends to also diverge. So that's why you can see here on this side you have large x, so your y is 0, and then it, as you go from right to left, you are increasing, and as x decreases more and more, it's increasing, and as you increase more, you can see the divergence. So as you go towards x is equal to minus infinity, the function will approach infinity. So this is the plot of this is the plot of y is equal to minus x. Okay, and this is the plot of y is equal to log x. Y is equal to log x, it's log x to the base e. Okay, so log x here is, so it should be your x, here x should be greater than 0, isn't it? Because as x tends to 0, y tends to minus infinity. This is the property of log. So this is what you see. So this is my y axis and this is my x axis. Okay, and here you have the 0 on the x axis, and here you can see that as you go from top to bottom, this part y becomes more and more negative. So you can see there is a divergence here, this part. Okay, so if you start from very close to x is equal to 0, that is the y value will be large but in the negative direction, and from there it will increase, and then you can see that this is not like exponential. Exponential is, you can see exponential is increasing very fast, like this it's going, right? It's going like this. This is fast. But here you can see there is some kind of like plateauing off. That is increase is not sharp. You can see it's going like this, as if it's going approaching a limit. Okay, so why is it like that? So from x is equal to 0, it's minus infinity, it's increasing as we increase x, and after that it keeps increasing, but it's not, here you can see the increase is very sharp, and after that as you increase x, the increase is not very sharp, it's some kind of plateauing off. That is, the increase is not, the rate of increase has come down. So what is the logic behind this? So for that I have to just see the rate of change of log x with x, rate of change. So rate of change, how do I calculate? ddx of ln x. What is ddx of ln x? ddx of ln x is 1 by x. So what does this tell us? So this is the rate of change, which tells us that if x tends to 0, 1 by x is okay, let me use the eraser. So 1 by x tends to infinity, isn't it? That's what we are seeing here. So the rate of change is extremely sharp, almost infinity, when x is close to 0, and after that when x tends to infinity, 1 by x tends to 0. Okay, so that tells us that as we increase x, the rate of change approaches 0. As I increase x, the rate of change approaches 0. And that is what we see here. If you go to the graph plot, you can see here. So very sharp increase, very steep. You can see this is steep, and here after that it's not that steep, and it's becoming flat. It's becoming flat, and as you increase x, you will see it will become more and more flat, and that is what I meant when I said it's plateauing off. Okay, so this is the plot of y is equal to log x. Then we are going to plot some other functions, like this is, we are plotting hyperbolic functions. Y is equal to sine hyperbolic x. So this is my y and this is my x. Okay, and this is my 0 on the y-axis, and this is the 0 on the x-axis. Okay, so what is a hyperbolic function? A hyperbolic function is defined like this. So when I say y is equal to sine hyperbolic function, I actually mean this function, e to the power x minus e to the power minus x by 2. Sorry. So this is the function that we are plotting. Okay. So one thing about this function is you can see that if x goes to minus x, then what happens? E to the power x minus e to the power minus x by 2. That is, I am changing the coordinates. I am just flipping the coordinates of x. Then this becomes e to the power minus x. X will become minus x. So this x will become minus x, and this x will become minus x. That means this will become e to the power x by 2. This is my y, right? The whole thing is y. And what is this? This is minus y. This is not. So if you just, so this is actually equal to, this is equal to e to the power x minus e to the power minus x by 2, and there is a negative sign, and this is minus y. So what it means? It means that whatever I get in, so I will just, so whatever I get in x, so you can see the plot. So this is my, so this is my, so this is x is equal to 0 line, x axis. So this is, sorry, this is my y axis, x is equal to 0. This is x is equal to 0 line. So on this side, x is positive. So this is x positive side, and this is x negative side. And this is my x is equal to y is equal to 0 line. So this is my, say, y is equal to 0 line. Okay. So you can see the plot of this hyperbolic function for the positive. So here you can just check. So here it's like this. So here it's like this, right? It's going up, and so this is for x positive. So immediately I can tell what will be x negative. X negative, when x for x negative, it will just be this thing with on the negative side because of this. If you just flip the sign of x, what happens is that only the sign changes. So such functions, so this is an so sine hyperbolic x, sine hyperbolic x is an anti-symmetric function, or I will not use anti-symmetric, is an odd function, I will say. Is an odd function. Okay, what is the odd function? A property of odd function is f minus x is equal to minus fx. This is the property of odd function. Or fx, so f minus x is equal to minus fx. This is what is happening here. So if I know what is the plot of my hyperbolic function between 0 and infinity, I can easily say what will be the plot of the hyperbolic function between 0 and minus infinity. It's just be this thing reversed. Okay, this thing just reversed like this. Okay, so this is the sine hyperbolic function is actually, let me just change the color, is actually an odd function. And you can see this property of sine hyperbolic function. So at x is equal to 0, at x is equal to 0, this is 0. So at x is equal to 0, y is equal to 0. Clear? And when x is much larger than 1, y behaves as e to the power x, because e to the power x, if that is true, the e to the power x is much greater than e to the power minus x. Okay, so at x is equal to 0, y is equal to 0. So you can see that is happening here. Okay, so at x is equal to 0, y is equal to 0, and at very large x, means when x is very large, then what happens? Y behaves as only e to the power x, and we have seen the graph of e to the power x. This is e to the power x. Okay, this is e to the power x. Okay. And why do I say so? Because at very large x, e to the power x will be much greater than e to the power minus x. Because at very large x, e to the power minus x will be almost 0, where e to the power x will be a very large number. So that's why we can neglect e to the power minus x compared to e to the power x. And so what we will get is that very large x, y goes as e to the power x. So you can see this is the behavior of the function in 0 and infinity. So once we know what is the behavior of the function in 0 and infinity, we can immediately deduce what will be the behavior of the function between 0 and minus infinity. Similarly, we can define what is called a cos hyperbolic function. So cos hyperbolic function, so what we have defined here, we are plotting here is y is equal to cos hyperbolic x. Okay, this is what we are plotting. So this is my y, this is my x, this is the 0 on the x-axis, and there is no 0 here. This is the 1 on the y-axis. Okay, so let us see what is the hyperbolic function, cos hyperbolic function. So y is equal to cos hyperbolic function is defined as e to the power x plus e to the power minus x by 2. Okay, so this is the definition, and the same thing we will do if x goes to minus x, then what happens? E to the power x plus e to the power minus x by 2. How does it behave? So this x will become minus x, e to the power minus x, plus this will become, so this x will become minus x, so this here I will have x by 2. So this is the same as before, so this is also y and this is also y. So such a function is called, so here what we have is f minus x is equal to fx, because y, anyway we don't have to write that, so I just remove this. So what we have is this one. So this is called even function. Even function. So here you can see, if you go to this thing, so here from 0, x is equal to 0 to infinity if we draw, so the curve is like this on the right hand side. Okay, so this is my, this is my x is equal to 0 line. Okay, so on the right hand side the curve is like this, and now we know this y goes to y, that is f minus x is equal to fx, that is, this is symmetric. So whatever the nature of y here will be, on the left hand side we will have the exact same form. Okay, so here also we will have the exact same form like this, just like on the right hand side. So this is an even function. Cos hyperbolic x is an even function. Okay, and so this is the logic. So if you flip the sign of x, then nothing changes. Okay, so here it was y, here it was y. So it was like a, so here the same values. So whatever value you will have here, you will have the same value on the opposite side. Whatever value you will have here, you will have the same value on the opposite side. Whereas in the other case, whatever value you will have here for this, say for this x, for minus x, for this minus, you will have the negative value. Okay, you will have the negative value. So this is plus, this is minus, you will have the negative value, here you will have the positive value. Here this function is odd, here this function is even. So that is the logic. And at, you can see at x is equal to 0, x is equal to 0, my function is, what is the value of the function? At x is equal to 0, 1 plus 1, 2 by 2, that is y is equal to 1. You can check that. So these things you can check. See, here we have at x is equal to 0, y is equal to 1. So, and this is my tan hyperbolic function. Okay, so this is, here what we have plotted is a tan hyperbolic function. So this is tan hyperbolic, so this is my y and this is my x. Okay, so here we have the 0 of y and here we have the 0 of x. So what is tan hyperbolic function? So what we are plotting is here y is equal to tan hyperbolic x. And how do I define tan hyperbolic x? Tan hyperbolic x is tan hyperbolic x is equal to sine hyperbolic x divided by cos hyperbolic x. And if we remember the definition, it is e to the power x minus e to the power minus x by 2 divided by e to the power x plus e to the power minus x by 2, which can be written as e to the power x minus e to the power minus x divided by e to the power x plus e to the power minus x. Okay, and now again we do the same thing. So e to the power, so x going to minus x, what happens? E to the power x minus e to the power minus x divided by e to the power x plus e to the power minus x. How does it change? It becomes e to the power minus x. This x will become minus x minus, and this x will become minus x, so minus minus is plus e to the power x divided by, here it will be e to the power minus x plus e to the power x, which is actually minus of e to the power x minus e to the power minus x divided by e to the power x plus e to the power minus x. So you can see, if this is y, this is just change sign, this is minus y. So I can write tan hyperbolic x is an odd function. That means is an odd function. That means if I go to tan hyperbolic, so this is my y is equal to 0 line, and this is my x. So my x equal to 0 line is important. This is my x equal to 0 line. This is my x equal to 0 line. So if I know the nature of the plot on the right hand side, so this is negative x, this is positive x on this side. So if we know the nature of the plot on the positive x, we can deduce the nature of plot on the negative x. It will just be the opposite, because for this x, this is the value. For its negative counterpart, which will be say somewhere here, the value will be negative. That is, it will be in the other direction. Okay. So this is one thing, and another thing that I want to point out is, let me change the color. So as x tends to infinity, so as x tends to infinity, so I want to find out the nature of the curve as x tends to infinity, that is very large x. Then tan hyperbolic x tends to e to the power, so Yeah, it tends to e to the power x divided by e to the power x. Why? You can see for large x, this is, if you check the numerator, this is much greater than this term. Okay, much greater. E to the power x is much greater e to the power minus x. That's why we will only keep e to the power x. Similarly, if you go to the denominator, is the same logic. E to the power x is much greater than e to the power minus x. So I will only keep this term and ignore this term. This term I will ignore. Here also I am ignoring this term. So it becomes e to the power x by e to the power x, which is 1. Okay, so that's why you can see that this tan hyperbolic function is like, it starts from 0, because at x is equal to 0, tan hyperbolic is 0, and then it rises, then it plateaus off at 0. So this is, you can see, y is equal to 1. So here it plateaus off at y is equal to 1. And on the other side, it will become flat at y is equal to minus 1, because this is an odd function. So this is the behavior of y is equal to tan hyperbolic x. So we'll just stop here today. You go through whatever I discussed today, and if there is any problem, let me know. So feel free to ask questions, because asking questions is the most important thing. And from next class onwards, I will give you assignments, because the only way to learn physics is to do problems. So that is what we are going to do very frequently in these lectures. So that will be it for the time being. In the next class, I will do 3-dimensional plots and derivatives and discontinuity, etc. So till then, bye.